Hey everybody, welcome back. I think hypothesis tests probably trips up students of statistics probably more than like any other topic that we do. It seems to be really confusing to people, and I think part of the reason is it's usually presented like just a checklist of subtract this, divide that, see if this is in that range, and it's very a mechanistic kind of approach to doing something that I think actually is really intuitive and makes sense. So in this next video, I'd like to spend some time just talking about the logic of hypothesis testing, because I think once you get the logic, all those other details just fall into place. So the thing to know about hypothesis testing is that we're testing some kind of claim, some kind of statistical claim. Maybe it's the claim that a coin is an unbiased coin and that it's heads or tails 50-50. Maybe that it's the particular mean for the population is a particular number. Like let's say the average income in the US is $30,000. Somebody might make that claim and you want to test that claim. And the key insight, I think, for hypothesis testing is that this is going to be an exercise in devil's advocacy. What we're going to do is just accept that claim on a very tentative basis and say, all right, let's just presume that what you claim is true. Then if anyone would collect sample data, that sample data should kind of verify, maybe not exactly because, probabilities and all that, but should be kind of consistent with that claim. I mean, if it is true after all, then the sample data should kind of mimic it. And so what you want to do is then have just a range of plausible values that you would get from your sample that are consistent with that claim. And if you happen to get a sample that is way, way different from what somebody is claiming, well, then maybe you should just reject that person's claim. It just probably doesn't seem to be consistent with the data. The data are what, data are. Those are the facts. So you would reject the claim. You wouldn't reject your data, of course. So that's kind of the general big picture of hypothesis testing. So again, you want to test some claim about the population. If that claim were true, we'd expect samples to corroborate this. And then if they do corroborate this, good, your claim is still valid. But if your sample is inconsistent with the claim, then you reject the claim. So here's just a very simple example. Someone claims, like they give you a coin and they say, this is a fair coin. All right, so then in your mind you're thinking, all right, well, if it's a fair coin, then I should flip it a bunch of times. And roughly half the time it'll come up heads and half the time it'll come up tails. And if you know about, the binomial distribution, you can actually calculate probabilities. Like what's the probability 3 out of 5 times it'll come up heads, or 2 out of 5 times it comes up tails, or something like that. But certainly if you were to flip a coin 5 times and it comes up heads all 5 times, well, that's a very low probability event. I mean, if it were true that the coin was fair, then what is the probability that you would get 1, 2, 3, 4, 5 heads in a row? That probability would be 1/2 raised to the power 5, which, if memory serves me, is somewhere around 3%. Which is to say, it's kind of unlikely that a fair coin would give you 5 heads in a row. No, I mean, it could happen. In fact, it will happen 3% of the time. But you're just kind of thinking, maybe this is a trick coin. Maybe it's a double-sided coin, or whatever they call it when both sides are heads. So on the strength of the sample evidence, you might reject the claim that someone made that the coin was fair. So that's kind of the general idea. All of this hypothesis testing stuff kind of hinges on the scientific method, on the idea that scientific claims, really what makes them scientific is that they are, at least in principle, falsifiable. Right? Where you just make some kind of claim that, Well, it could be true, it could be not true. You could maybe have some kind of experiment, and you might disprove a theory. Now, you can never prove a theory. You can just have a whole lot of supporting evidence for it. But it's a whole lot easier to disprove the theory. If your theory predicts that something will happen, and then it doesn't happen, you've just eliminated that theory. So the scientific method really is, the centerpiece of the scientific method is coming up with experiments that could potentially disprove your theory, this falsification idea. It's not the idea that you're verifying a theory, because there could be lots of different competing theories that give you the same conclusion. For example, flat Earth, right? Both the flat Earth and the round Earth gravity-centric theory says that, you know, if you jump, you go back down. I haven't proven anything by jumping up and coming back down. But if you circumnavigate the world and you head east and then you arrive, you know, from the west, then you've just falsified one of those two theories. You've just falsified the flat Earth theory. So more specifically then, what are the stages of a hypothesis test? Well, the first thing is you want to be very specific about what that hypothesis is. So maybe it's the hypothesis that the coin is a fair coin, so that the probability of heads is exactly 1/2. Or maybe it's a statement about the U.S. population distribution, that maybe mean income in the U.S. is $30,000 a year. Right? Somebody makes a claim. For the rest of the lecture, like slides here, I'm going to focus on these kinds of claims. Claims that the average of something in the population is a specific number. We're going to call this claimed hypothesis our null hypothesis. It's our starting point. It's our zero. And we're going to presume this guy is true. Now we need an alternative to that, right? So you have to compare one hypothesis with something else. And we call that the alternative hypothesis. And it is the logical complement of whatever your null hypothesis is. So it might be that the probability of heads is not equal to 50%, or that mean income is not 30,000. It's the logical complement of the null. So at least let's be very clear on what it is that we're testing. The next question to ask yourself is, what is your evidentiary burden? In other words, how much evidence do you need to collect that contradicts this claim before you're willing to just throw the claim away and say that was a nonsense claim? Notice this isn't really a statistical question, or at least one that doesn't depend on any data. It's a question of like the judicial system. See, we're going to have this null hypothesis, this presumed claim, and in a jury trial, we're presuming that the defendant is innocent. And then the next question is, all right, well, what does the prosecutor need to do for us to reject this person's innocence and, you know, throw away that claim and go for the alternative, namely that the person is guilty? That's determined, well, in you know, the U.S. judicial system, for example. It's independent of the data, but if you've got a criminal trial, then you need to make your case beyond all reasonable doubt. Right? That's the evidentiary burden in a criminal trial. In a civil trial, it's a much lower standard of evidence that you need to present. There, it only needs to be what's called a preponderance of the evidence, which is to say a little bit more than 50%, and you've won your case in a civil trial. In a criminal trial, they got to have a kind of a slam dunk against you. That's decided before you run the trial. You can't just change the rules of the game once the trial is underway. That's just not fair. That's a kangaroo court. So from the get-go, you want to know, what's my evidentiary standard? It can be, you know, beyond all reasonable doubt, which is to say, let's say 99%, like a 99% confidence interval. In hypothesis testing, we opt for 1 minus the 99, so this would be a 0, 1, and it's called a 0, 1 significance level rather than a 99 confidence level. But we establish that ahead of time. The other common ones are the 5% significance level, corresponding to a 95 confidence level, or the 10%. So you need to kind of decide what is your evidentiary burden. You got to pick one of these before the trial starts. Then we would need to translate this kind of broad stroke evidentiary burden, translate that into predicted, like allowable values that are consistent with the null. So in other words, how much evidence do you need? Like, let's quantify that. Not just say a whole bunch, or not even say 99%, but a sample of how many things with an average that's how far apart from the truth or from the claim. Let's figure that out too. Again, before we've ever collected any sample data whatsoever. So we're just laying out our plan of attack. Okay? And we're going to do that with what are called critical values. So in other words, you've got some claim. We're going to presume that that claim on the population average is true. If it's true, then we would expect sample averages to be normally distributed, and, well, 95% of them would be within 1.96 or negative 1.96 standard errors. Or if we normalize this thing, it would just be between a z-value of 1.96 and negative 1.96. These values here, those are called critical values. And they kind of determine the bounds of what you consider consistent with the null versus inconsistent with the null. So inside these critical values, it's consistent with the average. You would expect some plus or minus. So you call that the acceptance region. Outside of these bounds, these are, notice, really low probability events. They're in the tails of this distribution. These are your two rejection regions. And here, your rejection region. Again, we haven't collected any data yet. Now it's time to collect data. So in what could be thought of as the second large part of a hypothesis test, you finally run your experiments, you collect data, you get your sample. From that sample, we calculate some kind of statistic. It could be the mean. Like maybe you asked 100 people what their income is and you see whether it's very different from $30,000. Right? It could be, like I said, just a sample average or a normalization of the sample average. So some z-value that you got from that sample average. Your next, and this thing is called a test statistic. It's the summary that you get from your data. So gather your data, summarize your data, and then ask yourself, is this statistic that we calculated, is this sample average different from what you'd predict? Right? These are the range of possible sample averages that we would get if this null hypothesis were true. So our question then is, given this test statistic, does this guy fall in the rejection region or the non-rejection or acceptance region? So you go back here and you see, well, where did this guy fall? We had coin flips that were very different in the low end of things and one of the small tails. Then we would we would reject. We're in the rejection region. And so our sample information from our t-stat, our test stat, is way out in the tails, the low probability part of this distribution. And so maybe this distribution isn't right. Maybe it's not centered above. Maybe the true population isn't centered above this particular mean. Maybe it's something else. Or you collect your sample of incomes, and let's say they're really low. You ask 100 people, and their average income was $10,000, and so you're way out here. Well, again, you'd be in a very low probability part of this distribution, and so you would be in a rejection region. Is the sample evidence in the rejection or the acceptance region? That's this part here. And then finally, wrap it up. So if it's in the rejection region, if you got 5 coin flips in a row, you would say, no, this is not a fair coin. Or maybe you took a sample and the income was, 31,500, and that's within the range of acceptable estimates. Then you've, not proven your claim, but you can't reject that claim. So you just kind of stick with it. So those are just the broad strokes of how a hypothesis test is conducted. Now you might be asking yourself, how is this different from a confidence interval? And I'll just say right from the bat, it's very similar. Confidence intervals and hypothesis tests actually kind of serve the same purpose, and they are both kind of founded on this idea of a range of plausible estimates. Now I'll provide a link somewhere up on top where I go in far more depth about how these two things are comparison and contrasted with each other. But I'll say this right now in this video. They're both intervals. A confidence interval is an interval around the mean. So you have your mean, and then you add and subtract, let's say 1.96 standard errors. That's your confidence interval. A hypothesis test basically takes a claimed mean for the population and adds and subtracts a certain number of standard errors. All right? And then you both use them to verify or to judge claims. So in a hypothesis test, you start off with your data, you get your range, and then you see whether some claim fits in this range. And if it does, it's consistent with your data. With hypothesis testing, we constructed this entire interval before we'd ever collected any sample information. Then, after you've got the bounds of a test, you've got all your jury trial parameters set up, then you take a sample and you see whether your sample fits in with this range that's constructed around the hypothesized mean. So again, they're very similar concepts. I invite you to check out that video. And I'll say this, just like with anything, practice helps. So I'll have a whole bunch of videos coming up soon on practicing actually conducting a hypothesis test so that it's not quite such a vague idea that we're talking about, but a much more concrete set of steps. So I'll see you next time. Thanks for listening.